In this lecture, we're going to talk about factors that can speed up how fast enzymes are catalyzing a reaction. Okay. I have this zoomed out a little bit on this note page because I want to show you just a quick demo first. All right. So let's say that we have a molecule and it looks like this. So this molecule is a substrate. I'm just going to put an S on it for substrate. And we need to break down this molecule into two smaller molecules. This is the reaction, okay? Now, my substrate's gone, but in its place, I have the products, okay? My hands are like the enzyme. So here's the substrate. If I bind to it, I can cause that reaction to take place. Substrate's gone, and now I have the products, okay? Now, the speed at which I make products can be called the reaction rate. So here I'm going much faster than what I've been going previously. So my speed of my reaction was about this fast. This is about how quickly I was able to make a product. Okay. All right. So that's what we talk about when we're talking about reaction rate, is like how fast our substrates are being turned into products. Okay. Now, the speed of our reaction can be affected by different factors in the environment. Okay. Before we write anything down, I just want you to think about what you just witnessed here. Imagine if I had my substrates here, okay, and I had one here and I had more, but like this one I put in the office, this one I put in the gym, this one is in the parking lot, okay? So my substrates are all spread out in different locations, only this one is in my room right now, okay? So if I'm an enzyme and I'm going to cause this reaction to happen, think about how long it would take me to break all four down, okay? I would break this one down, but then I'd have to go way to the office to get the next one. And then when I have it, I could break it down, and then I'd have to run to the gym and get one. Okay. So my reaction rate, me being able to break or rip apart these pieces of paper, would be incredibly slow. Okay. Versus what if we had all of our substrates very concentrated right in front of me? Okay. They're all right here. All I have to do is pick one up. Okay. And so here's my reaction rate. Much faster because my substrates are all concentrated. Okay. All right. Now, imagine if I try to catalyze this reaction and my enzyme has been denatured. So it's the wrong shape. Okay. Now, my enzyme with its different shape looks like this. I won't be able to use my thumbs. Okay. So now that my enzyme has had a shape change, it's been denatured, all right, let's see what would happen to reaction rate. Well, obviously, I'm going to have a little bit more of a difficult time picking up my substrate, binding to it, and catalyzing the reaction if my enzyme is a different shape. Or imagine if I put gloves on, right? My hands are a different shape. It's definitely going to slow down my ability to tear this paper, okay, or create a product, all right? And then I want you to envision this. So what if we have plenty of substrate, so lots of substrate to tear, okay? And what if I pick up one and tear it and I invite some people in the hallway to help me? So all, five of us are standing around just tearing substrate. We would tear a lot of substrate in a very small period of time, okay? So the amount of enzymes that we have can affect reaction rate. All right, let's go ahead and put some stuff down now in our notes. Okay. Move this up a little bit. And here we go. Okay. So one thing that can affect how fast reactions are taking place is temperature. Okay. If we change the pH of the environment, it can affect how fast reactions are taking place. Okay. I kind of just showed you if we change how concentrated our substrates are. So substrate concentration can affect rate. And then also if I brought in more enzymes, we definitely will be able to go faster. So enzyme concentration can affect reaction rate, okay? let's just start with these two at the bottom and make sure you understand why we see this change in rate as we're changing substrate concentration, right? So this is basically showing you, here's your enzymes, and it's showing you that we don't have a lot of substrates and low concentration, okay? So my rate, my reaction rate, so how fast I'm making those products, is pretty low, right? Now, it's low because it just takes longer before the enzyme can bind to the substrate if there's not a lot of substrate to bind to, okay? But here's my enzymes. I still have 3. If I concentrate the substrate, it's going to take less time for our enzymes to bind to the substrates and create the product. So we have a much higher rate if we concentrate those substrates. Okay, now this next part. Notice my line flattens off. So let's think about this. Let's call right here concentration X, okay? And here is what I'm going to call the max rate, because that's the highest that our line has got right here. Max rate, because this is reaction rate, okay? And this is the highest point on this line. So basically, it means this. If I have a high concentration of substrate, I'm going to put a lot of papers right here, okay? I will start tearing one at a time, and eventually I'm going to be as fast as I possibly can. I'm tearing them at the highest speed possible, okay? Now, if someone puts even more substrate on my desk, I won't be able to go faster than my maximum rate. So even if we up the concentration even more, we set up a reaction with even more. So here's my concentration is now Y. We're still going to have the same reaction rate as we did at concentration X, simply because enzymes can only bind to and release those molecules at a certain speed. And just giving them more to deal with can't make them go faster. It's kind of like with homework, right? You can only do homework so fast. And if I give you more, it can't make you go faster or past your top speed that you can do your homework, okay? All right, so let's just put in here. As substrate concentration is increased, reaction rate increases, but then it will eventually level off at a maximum rate. So let's put then levels off at a maximum rate, okay? And this just explains why. Enzymes can have a maximum rate in which they combine to and release those substrates. So just by giving more substrates isn't going to make them go faster than their highest rate, okay? All right, so let's think about this. Let me put my substrate back here. Imagine if there is no enzymes, no hands. Then how many reactions would happen? 0. So my rate would be 0, okay? The speed is 0. Nothing's happening. All right. So if we have 0 enzymes, then my rate should be 0. If I add more and more enzymes, then my rate should just keep going up and up and up, okay? So this is like bringing in one person tearing paper, and then imagine if we have 2 people tearing paper. Imagine if we have, looks like it's showing 6 people tearing paper. Obviously, we would get a higher reaction rate if we have more enzymes. So as enzyme concentrations increase, reaction rate increases. Okay. All right, let's talk about the temperature and the pH. So in previous classes, I showed you guys some videos and some demos in which we altered temperature, we altered pH, and it affected the proteins in an egg. Okay. It caused those egg whites to turn white. Okay. Now, to show you temperature, I'm going to pull over this animation, because I think this makes it really clear as how temperature can affect reaction rate. I'm going to go ahead and I'm going to put plenty of starch. I'm just going to put one little enzyme in there. None of that one. I'm going to show you what is happening whenever we have a solution where the temperature is low. Okay. All right, so here we go. Let's run this simulation. Every time this enzyme hits a substrate, it'll turn into product. So right now we've had 1 reaction. So right now my rate is like, all right. So now we've had another reaction. So this reaction is happening, but it's happening really slow, okay? I'm going to pause and reset it. This time I'm just going to The only thing I'm going to change is I'm just going to up the temperature a little bit. Okay, let's put it at 40 here. Let's see how we do. Okay. All right, notice what happens when we increase the temperature. All right, you see our molecules are moving around a lot faster. Okay, so when we added that heat energy, then we increase molecular motion, and that reaction's already done. Okay, so obviously this reaction happened much faster, right? But let's talk about what happens if we go up even more. So let's crank that temperature up. Reset. Crank that temperature up. Let's run that simulation. Now they're moving even faster and they're colliding more often. But notice that whenever they collide, we're getting no product. Okay. So our reaction rate, the speed of this reaction is 0. We're getting 0 products in 10 seconds. Okay. So my rate is 0 in this case. All right. Going back to our notes here. So hopefully this now makes sense. So at a low temperature, we're going to have a really low rate, and you should be able to explain why. It's simply because our substrates and our enzymes aren't colliding as often, so we're not going to get product as fast, okay? But if we up the temperature, you can see that our rate has gone up. We have a much higher rate now that we up the temperature. We're going to increase the number of collisions that are happening in a period of time, so we're going to get product a lot faster, okay? But then let's talk about over here. So let's get that temperature even higher. And you can see at really high temperatures, like around 64, what is my rate? My rate is 0. I'm having no reactions taking place. Even though my molecules are moving around faster, we have denatured our enzyme. It had a different shape, so it can't function. So therefore, rate's going to drop once you get past an optimal temperature. So that enzyme, or this enzyme in this graph, works the best. It has the right shape to catalyze the reaction at 40 degrees, okay? If you go much higher, you're going to see that our reaction rate's going to drop because those enzymes exposed to those temperatures are going to have a change in shape, okay? Notice that this pH graph is also really similar in shape to the temperature, okay? But it's not due to molecules being slow and then speeding up and colliding more. Let me pull this back over here again, and we can alter the pause and reset. We can alter pH, okay? So I'm going to have the temperature, be here. Let's put let's run it like this. So it looks like I have a pH of 7. All right, looks like my reaction is happening pretty well. Let's pause and reset. And let's put my pH really low. So we're going to make this solution real acidic. Yep, my reaction rate is going to be low. It's going to be 0 just because we have changed the shape of the enzyme. And if I pause and reset, notice they're not going any faster. Okay, I haven't changed temperature, so they're still moving the same speed in all of these 3 simulations, but we're still getting no reaction because at a really high pH, our enzyme is denatured, so the substrate can't fit, okay? All right, back to our notes here to finish up this page. So as pH increases or decreases from an optimal pH. So for this enzyme that is catalyzing this reaction, it looks like it works really well at 8. If you increase or decrease too much from 8, the reaction rate drops. The reaction is going to happen a lot slower, okay? All right, so at that right pH, the enzyme has the right shape. Get too far away from that optimal pH, the protein will denature and it can't bind to the substrate. Okay? All right. Now a little bit of math. We're talking about reaction rate, which is how fast this reaction is taking place. Okay? The formula for reaction rate, remember, rate equals speed. So let's put speed down here. If I asked you to tell me your speed to school, you might say 30 miles per hour. And I'm showing you this because I know that you could tell me this if I asked you how fast you were going. And when you do that, what you're telling me is that hour or time is on the bottom in this formula, okay? So when we do rate, we always have a change in time is going to be on the bottom. And then we're going to have a change in something else at the top. Whenever you're talking about speed that you're driving, it's your change in miles. So you're at mile 0 to start, and then let's say you're at mile 10. and you then how much time it took to get there goes on the bottom. So we're just going to put a change in something because we can calculate rates of lots of different things, okay? But time's going to go on the bottom, okay? Now, we can calculate reaction rates by monitoring one of two things. If we have a device that can tell us how much H2O we have every second, that would help us calculate rate, okay? So in this case, this is the substrate and this is the products. Or we could have a device that maybe could measure how much oxygen we're getting made over time. That's a product, okay? So we can measure how much product we get over time, and we can use that to calculate rate, okay? Now, one thing about this reaction is, remember, this is our reactants on this side. This arrow means these things are being made. These are the products, okay? If I put H2O2 in a reaction, okay, or sorry, like in a graduated cylinder, and I add an enzyme, then we're going to end up getting these products, okay? You need to be able to tell me that H2O2 is a reactant, and if this reaction, so if I put an enzyme in with some H2O2, the H2O2 is going to disappear. So in a reaction, the reactants will disappear. Their number is going to decrease, okay? Or we can put will decrease because they're being turned into products. And over here, our products, this is what's going to be getting made from these. And once all of these have been turned into the products, you know, we won't have any. It's disappeared. And now we're going to have all products. So products will appear or be made, or you can say they will increase over time. Okay. All right. So if you look at these graphs right here, you can see that at time 0, we have a lot of phenolphthalein. Okay. And as this reaction is taking place, our amounts of phenolphthalein is going down until eventually it disappears. Let's go ahead and show that it reaches 0 there, okay? So in this graph, we are showing a change in phenolphthalein over time, okay? And since it's disappearing, this is showing us the reactants going down. We're going to use this to calculate rate. Over here, we have a reaction. Notice, here's my arrow. So anything on this side is the products. CO2 is a product. At 0 minutes, we have 0 CO2, but it's getting made. So this graph, we're monitoring the products being produced over time, and we're going to use that to help us calculate rate, okay? All right. So again, we're going to have change in something over change in time. Let's start with the easiest part. Let's talk about time, all right? Now, what we do, it says calculate the average reaction rate for the duration of the experiment. That is from our beginning to our end time, okay? So we're going to start with, we start at 0 seconds. And we're going to end over here at, let's say, 200 seconds. That's the whole experiment, okay? All right, now what we're going to do is we're going to put our concentration of phenolphthalein at those 2 times right over it. So at 0 seconds, my concentration of phenolphthalein was 2.5 moles. So let's write 2.5 moles right over that 0. And at 200, we were at 0 moles. Now all we got to do is do some math. So we will take 2.5 moles, we will divide it by negative 200 seconds, because 0 minus 200 is negative 200. And that's going to give us a decimal. Let me see if I can find a calculator real quick. Let's do this real quick. Okay, so then my rate would be, the reaction rate is 0.0125. Now let's talk units. All you do is write what you have here, moles per second. Okay, just like up here, I had miles per hour. Okay, all right. So let's do this over here. It says calculate the initial rate from 0 to 25 seconds. So this one's easy. It's telling me my 2 times. So let's put 0 seconds on the bottom. And then let's put 25 seconds. Oops, let me move this up so you can read it a little bit better. So we'll put 25 seconds there, okay? Now let's go to my data. At 0 seconds, we had 2.5 moles of phenolphthalein, okay? And then it changed at 25 seconds. So let's figure out my 25 seconds would be right here in the middle, right? So let's go up. And that's a good 1.5. So we're going to put 1.5 moles. Okay, so the molarity. And then we do our math. So this top number, we're going to end up with a 1m divided by negative 25. Okay, and that is negative 0.04, which brings me back to this. Positive divided by negative, I need to have a negative in front of my reaction rate. And what that tells me, if my reaction rate is negative, then that means that the slope of this line is going down. Okay, we're slowing down. Okay, over here, we have negative 4 moles per second. All right, you can take a second to try to do your average reaction rate. It's telling you from 1.5 minute to 4. Do it the exact same way. Put your time on the bottom. Find your other points from your y-axis. Put them on top. And do your math.